Hi, Dr. Lim and Mr. Key. Today, I want to share with you my prediction model on housing sales price. So first of all, I have to import the data and also the library. Then I realized that some data fields, they have null value. And also the target variable, the sales price, is a bit right skewed. So I have to transform them later on. Okay. Then in order to find out which features holds the most importance in affecting sales price, I have to use the correlation matrix and I pick them out. Then I see that the most important features are overall quality, year built, year real remote, ad, total business square feet, etc. Okay, then I look into them in details. Then I see that most of them have positive relationship with sales price. Okay, one of them that I want you to take note is the ground living area, right? As even though they have positive relationship, we see that there's two outliers over here. So even though they have high ground living area, right, their sales price is pretty low. So we have to remove these outliers to ensure that our model is more accurate. So for the first step of my data processing, I remove these outliers. Then I deal with the null values which some columns has. So I deal with those null values by looking at the data description text. Then I see, oh, that some null value I can replace them with an A or none. Yeah. Then some if it's a numerical, I will replace it with a median of all these value because the median accurately represents the middle because some of these numerical data are skewed. Okay. Then now there's no more null value. And I will remove the useless columns. So some columns have like no impact or like very little impact on the sales price, right? Or doesn't make sense, right? I remove it. Then for feature engineering, first I created some additional features. These features actually I thought of them. Then I think that they are going to affect the sales price. So I included these additional features such as square feet per room, total home quality, total bathrooms, etc. Then I encode the categorical data to dummy values so that I can encode it and train the model with it. Then for those numerical data that are skewed, including the sales price, the target variable, I normalize them using log. Okay, so now we see that the sales price is now normally distributed because it has been logged. Then I create models. So take note, the models I use, right, are all regression models, and there's some regularization parameter in it because there's a lot of features which I want to cut down on or remove them or have lesser weight on them. So the best model I would say I use is CatMoose because it has the best root mean square error. So I use root mean square error as a matrix because it's very sensitive to error, this matrix. So even though stack regression have the lowest root mean square error, because it's a stack model, right, it includes a few models, including CatMoose. So actually the best model is CatMoose. And it also has a lower standard deviation. Means that when doing the K4 cross validation, right, most of the result, the RMSE, right, are closer to each other. So the best model is CatBoost. So I use CatBoost. Then I further, see how it performs, and then I see that wow, the R square is actually quite high, which means that it explains very well. The model explains the data very well. So for the training phase, 99%, and for the validation phase, 93 only, because this means that there's some form of overfitting which we have to work on when we tune it later, hyperparameter tune it. So I try to tune it by adjusting these 4 parameters, especially the L2 regularization, because it has a lot of features, right? So if I increase this, right, it will smoothen out the model, and then it will actually put more weight on the more important features. So it works a bit, at least a bit. Then there's like improvement in the validation. So now it's 93% already, and the R square is 93, but there are still like some form of overfitting. So some extra things that we could have done is that we could have feature select some features that have no multi-collinearity issues. Right now, there's some features with multi-collinearity issues like total business square feet and first floor square feet. They share a high correlation, and I included both. So there's more features and it leads to overfitting. And in the future, I could also increase the regularization parameter. So in the CatBoost, like the L2 leaf are red, so it reduces overfitting. And in order to improve the model's accuracy, I could have included interaction features. Like sometimes there's interaction between this and this, right? Then the importance is quite high, right? I could have included these 2 interaction features inside to train as well. And some context feature, like such as like the distance from the bus stop, schools, eateries, shopping center, right? These are actually like, these can be the data can be included as well, but these have to be like further like get from the internet or stuff. Okay. And the test model, the testing is also accurate. And some AI ethics to consider is that because this is a housing sales price, right? If I predict wrongly, right, the severity is very high because it's a house, it's very expensive. So it could lead to financial loss if predict wrongly. And because the housing sales price actually is affected a lot by the country's economic. So it is likely that predict wrongly, especially at the start. So when I first deploy this model, when the company first deploy this model, they have to be human in the loop. Then when it starts to have confidence, it's mature already, then human over the loop. Then when there's no stakes, lower stakes, right, then it can be human off the loop. Some PDPA to take note is that even though there's no personal data, there can be some quasi-identifiers such as neighborhood and condition. Then because these fields, right, they are linked to individuals, right, that is able to identify them. So we can anonymize it or aggregate it, etc. And because like there's also some bias and fairness issue involved, because like some neighborhoods, some have some risk, more risk there, then some neighborhoods have more risk there. So like location features like neighborhoods, right, we must ensure that the data is diverse. And then after I train the model, I have to analyze that it is fair and it's not really affected by this feature. And now let's say look at this model's transparency and explainability. So I use feature importance and shared. So feature importance, the 5 most important features are such overall quality, high quality, and total home quality. You can see that some of these features, the important features, are the features I made myself. So this means that the features I made is quite useful in predicting sales price. Okay. Then this is also another B-swarm plot to show that the higher the overall quality, the higher the shared value. So the higher the shared value means the higher the sales price. The positive shared value means increased sales price, negative shared value means decreased sales price. Then now let's analyze one record. So this record, this is the first record, we can see that because it's built quite recently, it's 2003, it increased the shared value by 0.04, and it's the square feet for the area of the square feet for the house, right, is quite big. So it also increased the sales price. And but then you can see that the overall quality is not as good. So it decreased the sales price because it decreased the shared value by 0.02. So in this first record, right, its shared value is 12.26. It's still above the average. The average sale price is 12.021. The shared value is 12.021. So this is my model for predicting housing sales price. Thank you for listening.